Okay. Esteban, do you hear us? Jorge?
Yes, perfect. Let's get started.
Okay. Okay. Hello, everyone. This is Katarina from the communication team of WindEmpowerment. It's nice to see so many people here, many familiar names and many new ones as well. For some people who are new to WindEmpowerment, I'll just make a very short introduction. WindEmpowerment is an association for the development of locally manufactured small wind turbines for sustainable rural electrification. And we are a network of enthusiasts and organizations around the world sharing knowledge for empowering rural communities to build small wind turbines from locally available materials. And WindEmpowerment is organized in 6 working groups that are working on different aspects of rural electrification with small wind turbines. And one of our main activities is also a conference that we organize every 2 years. Until now, we have organized one conference in Athens in 2014, one in Patagonia, Argentina in 2016, and one in India in 2018. And WindEmpowerment also coordinates collaborative projects between different member organizations. If you want to find out more, you can visit our website or our Facebook page, also WindEmpowerment. Okay, that's all for now. Welcome to the webinar today. It is going to be about wind water pumping, and we are hosting Jean Alinei, Esteban Van Dam, and Jorge Ayarza, who will present us their experiences from 2 ongoing projects, WindEmpowerment collaborative projects that are funded by the SEPS program of Visions. Short intro about the presenters. I will skip the long bio. They are all experienced in manufacturing small wind turbines and training people to manufacture small wind turbines. Esteban and Jorge also run their own organizations in Argentina and in India, respectively. Jean is also the coordinator of the technology working group in WindEmpowerment, and he's also working on open source power converters. Today's agenda will go like this. So we will have 2 parts. In the first part, we will have a presentation of wind water pumping technical solutions. We will start with Jean with a project overview. Then Jorge and Esteban will present 2 case studies in India and Argentina. And in the second part, we will focus on the second project, which is about productive uses of wind water pumping. And it will be presented mainly by Esteban, and a short case study in India for productive uses. To help the webinar flow, I suggest to note your questions and remarks, and we can discuss them in the end. If you prefer to write the question, you can write it in the chat window. And one other thing is that the webinar will be recorded and uploaded on the YouTube channel of WindEmpowerment and will be shared on our website and Facebook page. So that's all. I give the speech now to Jean to start the meeting.
Can you put the presentation on in a mode that full screen, like presentation display? All right.
Do you see it correctly now? Do you see my screen correctly, guys?
Yes, yes, yes. Excellent.
So, okay, my name is Jean. I will try to, let's say, summarize briefly what happened so far in the wind pumping task force. WindEmpowerment started getting involved with wind pumping 2 years ago, supported by Visions, in a program that's called for knowledge exchange about this technology. And so I will start to present briefly the context of wind water pumping, and then I will let Esteban and Jorge speak about their case studies in their respective countries. That gives, let's say, practical cases of usage of such a technology. So to briefly contextualize wind pumping, well, wind pumps are usually well known in their American wind pump that you can find in every farms in remote America. It was like this application really boomed in the early age of the 19th century, where the green rush pushed the farmers to massively deploy this kind of wind pumps. And at that point, America had a network of manufacturers and spare parts that provided maintenance for this kind of wind pumps. So it was quite easy to deploy them and to maintain them. And then, like, the diesel generators arrived to the market and slightly destroyed this and eroded the market for wind pumps, because at that time, like, the oil was quite cheap, and it was way more like easier to pump water with fossil fuel rather than wind, because of this higher flow rate and better control on the water supply. And so the market slowly eroded, and yeah, when the fuel cost rose again, like after the oil crash in the 70s, then renewable started to be considered again for water pumping usage on the fields. But the thing is, solar won the competition against wind, because solar is easier to maintain and maybe slightly less expensive than the wind pumps. I mean, like, I'm still speaking about the American ones that you can see on the left side of my screen. So some really small wind facts. Wind energy makes sense only in windy regions, and like, small wind projects are only viable when you take maintenance into account from the beginning. A bit like the American example, where, like, wind pumps were really booming because of this good maintenance network. And wind is still a good opportunity when it's hybridized with solar, because it can reduce the cost of electronics and batteries and so on. So what's the strategy, and why do we want to come back in the wind pumping application now? Well, if we just give a look at this American example in the early 90s, they used, no, not 90s, but 19th century, sorry. They used this kind of multi-blade design that is really good when you are located in a not windy region, but in a mild windy region. And when it comes to high wind regions, where actually it makes sense to deploy wind turbines, the efficiency is quite poor for this multi-blade design, because they are designed to operate with high torque and low speed, and so they are not really suitable for high wind zones. If we go for the WindEmpowerment base design, that is a small wind turbine that are powering many batteries, they are called what we call micro and micro wind turbines. So they have a power rating that is located between 500 watts to 4 kilowatts. And so they are suitable both for wind home systems and small productive uses. So they are good for applications that range from off-grid and small DC appliances in the home to, let's say, small productive applications where you have like small motors or farm tools or stuff like that. So today we will speak mostly about micro wind that is deployed for a farm level application, enabling like productive application for the farm, for the water pumping, for the irrigation purposes. Why do we want to go for wind pumps with our electrical wind turbines? Well, first is our design. The Bigot design is suitable at the tip speed ratio that is around 5, and so it's suitable for high wind regions. It has the required robustness, so the maintenance is lowered compared to like multi-blade design that would wear and tears really fast in windy zones. This design is good for pico and micro scale small wind turbines, and it's using readily available tools and materials. It's used to make education in these remote zones, and so it's well known about the local communities where we have a local stakeholder that is giving courses to them and help them maintaining their system. So we already have this maintenance network in few remote areas where it makes sense to use the system as a wind pump. So when it comes about the water infrastructure, actually it's already deployed in these rural zones. So you already have wells equipped with pumps for the water supply, and you already have a watering infrastructure for agriculture. The thing is, what we want to do is to interface the actual technology that we have in WindEmpowerment, which is suitable for the windy zones, with the infrastructure that is already present on the field. And what we are trying to design in this project is the small interface, the missing link that is between the small wind turbine and the irrigation or water supply infrastructure. So what we first done in this project is trying to get a rough estimate of how many cubic meter we could pump per day with our wind turbine. So at the screen is a graph that is showing what would be the average flow with 4.2 meter wind turbine, depending on the water head, so for different situations. And so from these rough estimates and with the help of Alfie, we were able to plot, to make maps for both the Indian case and the Argentinian case that we were mostly focused on, that gave us the average cubic meter per day in a country. So basically what this map does is extracting the average level of the water table in the countries, and using the tables that I just showed beforehand and match them to give you the flow rate that you would get out of your wind turbine. So we see, like, actually I don't know if it's visible, but you have like two small cycles that cycle the zone where we are, that are our case study zones. And so we are trying to deploy two sites there and to check if these wind pumps are suitable for the needs of the farmers there. So to summarize the project's vision, like the vision is to create the interface between the Pigot wind turbine and the existing infrastructure on the fields in order to cover the water demand in these windy regions. The idea is to reduce the dependency on electrical storage, so to try to go for direct coupling between the energy source and the energy consumption in order to lower the overall cost of the system. And the idea is that this interface should be open source to be able to maintain it and to improve it in the following years. And still, yeah, to get to use the strengths that we already have because of our local stakeholders that are able to deploy this local network of maintenance and educated people around the technology. So we want to take profit of the WindEmpowerment network to promote this technology, this new technology. So yeah, this was my quick introduction to the project. Now I will let Jorge speak about the Indian system, the Indian use case.
Okay, thank you, Jean. I give the presentation to Esteban, right?
Okay.
Yes, I'm presenting Jorge's part, so let me know if, I mean, I'm showing slides. Jorge is presenting his part. Let me know if you can see it correctly.
If you can make the screen bigger, that would be good.
Esteban, go to slide mode. Excellent.
So yes, my name is Jorge, and I'm going to speak about the efforts that we're doing in India. We're actually, the project is based in Oroville, which is in the southern part of the country, in an area that's not windy. But our project site actually is in Karnataka. It's more in the south central part of India, which is a higher plateau, which has better winds than where we are located. So if you can go to the next slide, please. So the goals, of course, of the project, create infrastructure for local manufacturing, and we were successful in that front. We're obviously using local materials and trying to get the lowest cost option. In fact, in India, at this point, the lowest cost option tends to be the largest wind turbine that we make, which is a 4.2 meter machine, at least in the cost per watt basis. And the main reason for this is we're finding that it's more and more difficult to pump the water, and the depth of water is decreasing because there's a drought. We're dealing with very dry conditions, and about 70% of the water in India is pumped. So we don't have as many rivers as other countries in terms of at least the size of the country. And of course, we are also looking into using the existing equipment to do additional stuff other than exclusively water pumping. There's a huge need in India. There's about 25 million diesel pumps. So if you look at the market segment for India, the replacement of those would be an ideal target for the development of the technology. There's still large unelectrified areas. In most of the areas that are unelectrified till now tend to be a bit in the mountain areas and rather remote sections of the country. And even the sections that are served by the electric grid are actually underserved because the grid is irregular. There's not enough power being produced in the whole country, so we have blackouts regularly, and that makes it much more difficult to manage crops. And Of course, energy independence is a key issue, basically because of the unreliable grid. And the strategic importance that is becoming more and more important nowadays of local manufacturing. Can we go to the next one, please? So who was involved in this project? We have ourselves, which is called Minvayu, which is a project
Jorge, we cannot hear you now very well.
in Oroville, near Pondicherry, South India. We have our project site, which is, hopefully it's better now. Can you hear me? Hello.
It's a bit better,
Can you hear
maybe.
me?
Yes, yes.
So our other project partner is called Proto Village. This is actually a development project in Karnataka, which is about 3 hours north of Bangalore. And they're actually in the second driest area of India. So this is actually quite a challenging location. So there are partners not only in water pumping needs, but also in productive uses and additional productive uses. And of course, Visions is a funding agency and a support for the project has been invaluable, and of course, WindEmpowerment in general. I'm missing in this slide support that we've been receiving from University of Toulouse in France, and also support from Argentina with the collaborations we have there. Next, please. So what is the design? The design of the system we have is a direct drive AC water pump. So the only difference really from this design from a standard battery charging system is simply that the stator, the generator, is actually not being rectified to DC, but is generating the power in AC mode with 3 cables. And in essence, what you're doing is you're connecting those 3 cables directly to the pump. And the idea here is, and this is basically, you could say, the competitive advantage for small wind in this regard, is that you are generating a 3-phase alternating current, and that means you can connect directly to also a 3-phase alternating current motor or motor pump. So technically speaking, we can connect it directly. Obviously, there is a controller in between, but the controller is not rectifying, not producing DC power, but it's simply turning on and off the system. So there's only a simple contactor turning on and off the system. So we do not store the energy. We simply run the power directly from the turbine to the pump. The advantage with this, obviously, is we are using standard alternating current motors and pumps. So basically, you can retrofit the system that it's already existing. Of course, the size of the pump is important. Yeah, so we cannot run a motor and a pump that are excessively large compared to the size of the generator. And you are using a technology that's well understood, that is easily available, and it's easy to maintain. The other key aspect of this project in particular, but it's not exclusive, is the fact that we use the Hupigo turbine, a standard Hupigo turbine, and we just modified it partially, which is simply we changed the voltage of the stator so that it could generate the same amount of power and voltage that the pump will need. So there's minor modifications to the turbine. And well, obviously we had to develop a controller. So next slide, please. So obviously we're talking about direct drive. We are talking in our case in this project is we have a 2 HP or 3 HP motor pump. The the curves that you saw earlier with John were similar to the ones that we're using for our turbine, which is a 4.2 meter machine, and you can see that there will be a variation of pumping dependent on height and dependent on wind. So we're putting a 100-meter drop is a reference point, but this in reality will depend on the efficiency of the pump. So you will find pumps made worldwide that are performance, and you'll find the same pump with the same motor, but with a much better and higher quality construction, practically producing double or triple the amount of water. So in our experience, we are in Oroville at least, we have been using Danish pumps that are made in stainless steel, but the majority of India uses lower cost cast iron pumps. So what we did in this project is we actually used what is standard, and we're trying to get data from that type of pump. But we have actually not tried 100-meter depth wells, but in theory it could reach that. There's another aspect, and that's important, is the voltage of the system. And we in India are using 440 volts because the pumps that are sold in the market are 440. These are three-phase motors. And in other countries, maybe instead of 440, it will be 220. So obviously you would have to design the stator to match the pump, but everything else pretty much stays the same. The other aspect that's quite critical here is, if you look in the middle of the circle, is that we can run any AC pump. So the fact is, the most common pump that you find in agriculture are either centrifugal pumps that are surface pumps or submersible pumps. Here in India in particular, the most common one is actually submersible because, as I told you guys before, the majority of the water coming for farming in India is from wells. So these are sometimes quite deep wells. And lastly, the last pump is obviously a positive displacement pump. And there is one characteristic, is that the positive displacement pump, which is the one used actually in Argentina, is actually better suited for variable speed. So you could have higher efficiencies from those pumps, but the tendency is that they end up being a little bit more expensive than a standard pump. But fortunately, Esteban will talk to you about the pumps that they make in Argentina. But we are not, at this point, we have not tested our positive displacement pump, but we would love to. Next slide, please. Okay, the first system that we built was actually in village in Karnataka province, and a picture is actually of the project site. So we actually built the turbine right on the spot. So in a course of about a week and a half, we actually built a 4.2 meter diameter turbine and the tower. And we installed it in our first well. This included a 3 HP pump. So this was the existing system that was actually running on the site. So we simply connected to this 3 HP pump, and the depth of the well is around 30 meters. Yeah. And that's actually the the first installation that we did. Yeah, next slide. The next thing that we worked on is actually, and some of you may remember, we did some batch testing at NIWE, at the National Institute of Wind Energy in Chennai. And there's a picture of the device that we use for bench testing. And those were tests that were done on a 2 HP surface pump. Mainly the idea was to be able to check and see the operation of the stator, to look at the relationship of voltages, and actually be able to check the voltage to frequency ratio, which in these types of designs, this is the key area of design consideration. We have a 440 volt generator and motor that are working technically at 50 hertz. So the voltage over frequency has a ratio which is, in the case of India, it's 8.8. So as long as the generator is able to deliver the power at the same ratio, then we're operating just as a variable speed drive would operate a motor in an industrial setting. So a standard motor, a standard induction motor, let's say, if it's operating with a variable speed drive, it will operate correctly and it will not burn. Yeah, so this is the way the system is working in our case. Now in order to make everything run properly, what we knew we needed to develop is a controller. And actually, the controller is turning on the system so that the turbine gets enough spin and speed to rotate, and when you connect it to the pump, it's able to actually operate. The design of the controller, we needed to do it from scratch because these type of controllers simply don't exist. And so we're happy now. We're happily able to develop a controller with the support of the University of Toulouse, with Luis Villa as an advisor. And so with the WindEmpowerment network in France, we were able to actually develop and test this circuit. So this is quite important, the controller. The issue is if you do not time the turning of the pump correctly, you will not be able to operate the turbine efficiently. Basically, if you turn on the pump too early, you will stall the turbine. And if you do it too late, you will lose efficiency in the system. So what we've discovered at this point is actually we will need to further improve the startup of the turbine. And this is basically what's happened recently, because we had to change the site where we originally started. And I think we skipped one slide. Can you go back? Hello? Can you, yeah, no, so, okay, go further down, sorry. And the next one. Okay, the testing of the bench test, these are some of the values we were getting. And what we have here on the left is the power in watts. We were only able to run it. This is running on a 2 HP pump. Yeah. So we were getting liters per second on the right column. Yeah. So we were reaching up to about 3.5 liters per second at around 50 hertz, which is we can see there it's around 1,700 watts. So that's pretty much equivalent to what a 2 HP pump would need to operate. So the idea here is when we did these tests, we were trying to also relate the voltage to frequency, and in the original design, we were saying that our voltage to frequency ratio, instead of being 8.8, it was closer to 6. So the data design and the second and the field turbine to be able to have a higher voltage to frequency ratio, which would enable the turbine and the pump and the pump and the turbine to be able to run cooler. Can you go to the next one? Okay, so the second system, we started with one system, and because of the drought, the well dried. So we added a dry well. So as I said before, the project site is quite a difficult site because it's the second driest area of India, but on top of that, we had 3 years of drought. So one of the reasons that the wind turbine was installed was this is a system that was running on solar water pumping. But because of the drought, you had cloudy days with no rain. So after one monsoon without rain, they decided they would like to have a hybrid system to be able to handle the possibility of not having rain and having a cloudy season. So we run it as a hybrid system. Can you go back? Yeah. So the system started running in one well, but then it was changed to another well, which was actually a little further away. And this well is deeper, so we have around 60 meters in depth. So we've had to modify the installation from the original design and the original site. Basically, we have around 300 more meters of line, power line to reach the end of the land where the new well is located. And the idea when we had to modify everything, then what we've done is we've actually installed a new controller on this setup. So we've had to redo some of the settings, and we plan to work on improving the startup. The system does not have some running capacitors, and we're looking into the possibility of either adding capacitors or a mixture of capacitors and resistors to help improve the starting in the system. This is something that has not been developed yet, and so maybe this will be our COVID job to work, sit down for a couple of weeks and work on a new design of the starting system. Next one. Okay, that's it. I think it would be Esteban now that will talk.
Okay, everyone, can you hear me?
Yes, we can hear you.
Yes.
Okay, great. Let me share the full screen. There. So I'm going to talk a little bit about our case in Argentina and how we used a slightly different technology towards the same goal. So in our case, the goals were pretty much the same. We wanted a low-cost system that would work in our context. High efficiency. This is something that Jean mentioned in the beginning. So we're competing against other solutions, so it has to be very efficient in order to make sense. We wanted something that can happen locally, so we can not only build the wind turbines locally, which is already happening in many areas in Argentina, but also keep it for over the years in the long term. And we're very interested in particular in the productive uses of the energy. And this is something that we will go deeper in the second part of this presentation. So the main parameters to consider to design our system and to think which would be the best configuration for Argentina was first, how much water do we need? So first think where we're going to use the energy and then design a system that feeds the needs of water in the area and not more and not less. Which are the other solutions that are happening today, so that we know if our solution is an improvement or not against what is there today. Which types of wells we are working on, so where do we want to connect these pumps in order to design a system with the most appropriate pump. Again, what type of pump we're using, not only based on the well, but also on the general conditions of the area. And what type of use we're going to do with that pump. Cost and maintenance complexity, and of course robustness, so that this is a system that that has a long-term duration. So who has been involved in this? Of course, this was a project proposed by WindEmpowerment in one of our conferences, and we've been working since then with the support of Visions, as Jorge explained before. We're also working a lot with the CNRS laboratory in France. They are helping us with, particularly Jean today, presenting also from this laboratory. They're helping us a lot with electronics. We're also working close with a local university in electronics in San Luis province, which is LCA. They have been working very closely with the laboratory in France to develop a solution for our case in Argentina. And ourselves from 500 RPM, we are an NGO based in Argentina, supporting wind turbine manufacturer for rural electrification, and now very interested in particular in water pumping solutions. We're also working very closely with INTA, which is National Organization for Agriculture. So they have all the knowledge about which is the best way to use the water and to improve the mix, the match between the solution, the technical solution from the wind, from the water, and for the agricultural purposes, which we're going to speak more in detail in the second part of this presentation. So a quick diagram of the system, which is slightly different to the system that is being developed in India. In our case, we are rectifying, so we're going to DC from the wind turbine. Then there is a specific electronic speed controller that controls a DC motor that drives a pump, which is a positive displacement pump. So we are using a standard e-bike electric motor. So this is not something that we have to manufacture ourselves, but it's something that is existing in the market. It goes between 24 and 36 volts, so it's perfect match for 24 volts wind turbine. I mean 24 volts starter configuration. It is 400 watts, which matches very well the 350 rated power wind turbine, which is 1.80 meter rotor diameter. We are using a diaphragm pump, which is very standard in Patagonia. I'm speaking about Patagonia because this is the area where we are testing and doing our pilot projects, and it's where it makes sense, and I'm going to explain the context later on. Both the motor and the pump are quite low cost and locally manufactured, so it's easy to find, and some things that are already used in these areas. It's not like we're bringing a new technology. And there is this custom-made MPPT, which is the key factor of the whole system. It's something that will convert the DC generated by the wind turbine into DC to the motor, so that the motor will be requiring or operating at the frequency based on the wind speed of every instance. So it has to be changing very quickly. As the wind changes, the pump speed and the motor speed feeding the pump will be changing very quickly. So this is the key factor where we're working on with the team in France and the team in Argentina and San Luis, the electronics guys. And this has to be very robust. So this is where we are making our biggest efforts today. We're also developing a safety net, which is what happens if the thing fails. How do we protect the system? So, and how to make a diagnostic of where a problem might arise, which is very important for the system to work in the long run. So this is an additional thing that we are developing to make more robust the whole system. So which are the main specs of the system? It is direct drive, so there is no gearbox. We want to drive it directly. There is two wheels, so that there is a conversion in the RPMs. This is the picture in the center is how the diaphragm pump that we use looks like. It can pump up to 1,200 liters per hour with 8 meters per second wind or higher. So it's very standard conditions in the places where we're working at. We connected to a 350 wind turbine, the rated power of the wind turbine. The places where we are installing these systems have very shallow wells. It's not deep wells. It's usually from 10 to 20 meter wells. And sometimes it's a river going or a small stream going by. So we don't have this problem like they have in India of deep wells. That's why this type of pump is most appropriate, and also because it can adapt to different speeds. So it's more efficient when you change the speed. So if you have a few meters per second of wind, it will already be pumping something. That's not very common in Patagonia, but it will be efficient at varying span of wind speeds. And then there is the issue of the step, and this is one of the key issues regarding how to control the system. So basically, the MPPT will increase the step of power required by the water pump by increasing the speed. So you have to measure, you have a time step. Let's say you will measure every second, and if the wind is going higher, then the system will know because the speed is speeding up. So it will speed up also the motor, and this will keep controlling itself. So once the load is too hard on the system and the pump is loading too much for the wind that you have, it will automatically start to slow down. And as the wind speed goes down, the pump speed will go down, and the controller will then reduce the power of the motor. So it will keep in this loop until, independently of the variations of the wind speed. Now, the main issue is how long these steps are and on what is the best time step to use on these systems. So this is what our first prototype looks like. On the left of the picture, you can see the motor connected on the side on the right to the pump. Right below, you have the controller in the bottom left corner. So there were some pros of this first prototype. First of all, there was a perfect match between the wind turbine in terms of power and voltage, and the motor that we were using, the brushless motor, DC motor, and the pump. So the configuration proved to be very good and a good match between the three components. And it was very cheap system. Now, the cons that we had was that this first controller that we developed before working on this present project with WindEmpowerment was not open source, so we were finding it hard to keep improving it. We couldn't find an ideal step to make it work. there were too many stops when the wind was speeding up. The system worked well, but as the wind started to go down, the load was too hard and the full system stopped. So it was running and stopping very frequently. So it did work, but it was not very efficient. In the end, we were not pumping a lot of water. So this is why we started this new project to improve this. So we are right now working on the second prototype together with the French and the Argentine teams, electronic teams. We are using the same motor, as it proved to be a good solution. We are using the same wind turbine, and we're using the same pump. So this is something that has proven to work fine. Now what we are mainly focused on is to improve the MPPT controller. This is what is missing right now. There's a very good progress about it. Teams from France and from Argentina met in Scotland 2 months ago, and they came out with a solution that is almost ready to test. So this is the next step, testing this new solution. This new MPPT controller is more universal in the sense that it aims at being used with different pumps or different technologies, not just this particular configuration in the future. It will be way more robust than our first prototype, and of course more efficient, which was the main problem of our first prototype. Okay, I am going to pass on to Jean.
Okay, do you hear me well?
Yes.
Yes.
Right. I will put it full screen. Okay, so I will just add a bit on top of Esteban's speech to present like the actual power converters that we are trying to jointly develop together with the Sandwich University and the other exchange that we are doing with this technology. So the first picture you can see on the screen is something we are very proud of. The red board has been replicated in Argentina. So this is as a bare PCB, but like they really soldered all the components and they get their own copy of the converter just by themselves. We just shared the files and around, and they were able to copy it correctly. So we have like this nice collaboration that is getting on more and more. Like 1 month ago, we were in Scotland together and discussing about the technology and developing new applications together. So now I will just present you like what happened with this converter, what is its main purpose, and what will be the next step of its development. So just like a quick summary of what I will be saying, I will be speaking a bit of power electronics and what we are thinking of. I will also present the actual issue we are trying to tackle, and then what is the current status and what will be next. So to speak briefly about power electronics, well, power electronics is two nightmares combined. One nightmare is the hardware side and one nightmare is the software side. Well, usually the hardware is a black box, meaning that you don't know what is inside. And you have, if you go for proprietary converters that you can find around on the web or just buy in China or something like that, you will just find a box that is full of components. You don't have the schematics, you have a lot of wires everywhere, and then you have to figure out by yourself how to repair it, or how does it work, or how do you change this application slightly to modify some parameters. So one key aspect of the current development is making things open source, that we can share the knowledge, share how to repair the things and improve them over the time. So like this perpetual improvement is really the key, a key aspect of our joint collaboration. And so this is why now 4 years ago, we started developing our own power converters at WindEmpowerment, which aims at developing multiple applications around rural electrification and power sources. So the idea with the power conversion side is not only to perform conversion of the dealing with the wind turbine power flow, but also with solar power flow and DC and AC appliances. So here, like this converter that we developed was used to develop this new application with the wind pumping. So we wanted to connect the flow from the wind turbine to the motor. So just like to give you a bit level of abstraction of what we are developing, like the hardware is the one that is shown on the leftish and downish part of my screen, and then we have like the embedded firmware and software that are on a microcontroller on board, and then the idea on the long term is to deploy this high level of monitoring of the power converter to be able to store and share the data around the power conversion. So the topology that we use is a 3-leg converter. So why do we use such a converter? Because it's like a 3-leg converter is suitable for both 3-phase, monophase, and DC applications. So with these converters that I showed previously, we are able to like connect 3 different DC bus to 1 DC output, but we are also able to get 3 different output from a single DC input. We are also able to get 1 AC output, 1 DC output from 1 single DC input. And we are able to perform a 3-phase inversion. So that means that we can inject in a 3-phase grid or in a 3-phase motor. And we are also able to rectify the power from a wind turbine or from a generator or whatever, and to charge a battery, for instance. So in this project, the use of the converter, another key aspect of the converter we're trying to develop is modularity, meaning that one converter is a given power level, a power rating. But what we want to be able to do is to connect them in series or parallel to extend the possibilities in terms of current capacities or in terms of voltage capacities by coupling them. So far in this project, we are mainly focused on driving motors with it. So it means that we are developing the software that allows the power converter to run the application for the design application. So here are 3 pictures of us developing the technology. In the leftish eye side, we have all of us working in Glasgow when we met 1 month ago, trying to develop the code, the embedded code to run the motor. On the right side of the screen, you can see Jakobos, who is a new intern that is developing the functionality full time. Here is us in Glasgow. And now I will show you just 2 small videos for you. So here you can see the AC motor that is spinning at the beginning. So this would be for an application such as Jorge's one, where we could connect, where we would be able to connect solar panels to an asynchronous motor. And this is Argentinian case where we are running a synchronous motor out of the same converter. So just by reprogramming the power converter digitally, we are able to get 2 different functionalities, such things that we couldn't do with some things that wouldn't be open source and where we wouldn't be able to hack and transform ourselves. So now what the challenge is how to develop such a converter, because we are tackling different applications that have different power requirements. Well, actually, our view is to get a power converter that has an ISO power curve, meaning that for 1 kilowatt, we can get either high current at low voltage or low current at high voltages. The thing is quite complicated because if we look at this power plane, it's composed of 2 different zones. The zone with the low voltage, and high current, and the zone with high voltage and low current. Why there are separate zones? Well, because it's not the same components. You cannot just replace the software in such a way that you will get high voltage from low voltage rated components. So we have to find a solution to be able to evolve from the low voltage operating point and zone of a battery or a wind turbine or a solar panel to the high voltage zone of an AC or AC drive zone or an AC motor. Why do we want to do that? Because we want to provide the final user with different applications that will cover both the DC appliances for his home and the AC appliances for his productive farm or his productive applications, where you won't find suitable motors that are rated with low voltages. So in order to do that, and that will be future development, so far what we have developed is a low voltage inverter. So it means that we can go from a DC battery to an AC low voltage synchronous motor, or we can run an asynchronous motor but at low speed. But ultimately what we want to do is to be able to perform all the power conversion that I was speaking about in both the low voltage and high voltage range. And why we want to do that? Because then it will be quite easy to deploy on the fly these functionalities on the field, just because we just have to switch things digitally and not on the hardware side. So I will, if you want, I can explain a bit more in detail what it's about, but I will just give you an insight of what it would be allow us to do in the future in this precise application for wind pumps. So if we go for the Jorge system, for instance, so far he has a wind turbine that is shown on the leftish side, then he has his startup controller, and then it goes directly to his asynchronous motor. But what we want to be able is to insert in between our converter that would act as an open source VFD drive powered through photovoltaic panels, for instance. Or what we also want to do for the Argentinian case is to replace the proprietary Blackbox that we saw earlier with this open source electronic speed controller that we will be developing on the fly, and that you have seen spinning earlier in my presentation. So these are two different applications for wind pumping that we could be able to develop like quite easily with the hardware we've developed. So this is a conclusion. What we want to share. We want to share what we've done on the hardware side, and we want to collaborate to develop functionalities, software functionalities, to be able to provide a complete solution of power conversion for the stakeholders on the field that they will be able to deploy and to share with the local communities. So we are really interested in getting your feedback on this value proposition of this project, because I think it's quite new to get something that is completely open source, but that you can invest yourself in developing the software, and you can also get supported functionalities from the development side, from the core development team. But we also need people to test this stuff, and we are interested in gathering the data around this power conversion in order to extract like insights of how it's used and how to get better with the functionalities. So that's it for me.
Okay, great. Thank you, Jean. Should we continue with the second part, Esteban?
Or maybe we can do a short break by having a few questions, maybe?
Yes, that works also. Okay, let's do that. Anyone wants to ask something? The presentations until now?
Hi there. This is Noam from Comet.me. It's not a question, it's more like comments. So would you have some time later for, you know, broader discussion of the project?
You mean on the power conversion side or on the wind pumping, let's say, because they are completely joined. I mean that.
Right. You know, I have comments on different issues of this project, and I wonder, it's up to you if you have time to hear my comments.
Sure, definitely. Like
Yeah,
we are
right. You want to do it now? You want to do it later?
Well, maybe we have a few minutes now just to get like maybe an insight of your knowledge and that you can share your experience with us, and then maybe we will have maybe an extra time later on or program something just between us to discuss later.
So let's talk. Let's talk first about the controller, because this is what you presented. Okay. We at Comet have been developing a solar pump for more than 5 years now. It's a positive displacement pump driven by a linear motor that we have developed. I can share with you more information, or you can go to our website and see the actual material. One thing that we've learned through the years, and we've tried all different controlling systems, which actually refer both to wind turbine and solar energy. We've been active in the wind turbines for more than 10 years now. We are part of the WindEmpowerment Association from day one. So regarding the controlling system, in our view, AC motors, off-the-shelf AC motors, are not adequate for renewable energy because they need to run, they developed and designed to run in a specific frequency and specific power. And once the power, whether it's solar or wind, changes, you need to change the frequency and the power, and they're not working in the optimal point. As a matter of fact, the world is going today into brushless DC motors whenever it relates to renewable energy. Mostly
I completely agree on that, but the thing is, like the idea is not really to go against this new trend going synchronous. The thing, and instead, the thing is just to comply with what is already present on the field. Like to have both possibilities. I mean, if you already have a watering infrastructure that is underlying on an asynchronous pump, we want to be able to connect it directly with the wind system. even if it's
Okay.
not completely optimized, of course. But the idea is not to go for the technical optimization, but rather to the socio-technical optimization, where, for instance, if you have some productive uses in mind, you won't be able to change the motor of your application to go for a synchronous motor if you already have another different technology. So we want to have both possibilities, to connect it with low voltage synchronous motors, but also to connect it with asynchronous off-the-shelf motors.
Okay, I totally agree. But let me go on a little bit, okay? There are two options here, okay? One option is to run some kind of maximum power tracking mechanism, whether it is solar or wind, to harvest maximum power from solar or wind into your motor. The other alternative, which is what we are doing today, is to control the motor according to the input energy. And this is a completely different way of doing it. Because if you look at a motor driving a pump, it needs to work according to a specific load, which is the pump head and varying pressure. I don't know what the pump is connected to. And the load dictates the current. The more power you have, you can run the motor faster, so it provides higher flow. So what we are doing is we developed a controller that is actually looking at the input power and controlling the speed of the motor according to the input power, providing enough current to overcome the load.
Hey, no, I'm Esteban here. That's pretty similar to I know you've been doing this with solar, and this is pretty similar to what we are doing with wind in our case in Argentina. I think that the main reason for different systems is because there are different needs. So I would like, if you don't mind, to move forward to the second part of the presentation, and then we can discuss this in deeper detail in the questions part, if you don't mind.
Esteban, I appreciate your comment. I think it doesn't involve most of the people around the forum right now. But what I would like to do, if with your permission, is to set another meeting just with the people really inside the internal loop to discuss different architectures.
Yeah, that's exactly what WindEmpowerment is about, and we would really appreciate to have your input, because even if you've been working mostly on solar in this aspect, I think there are many things that can be shared between the two technologies. So definitely, let's organize a meeting later on to
excellent.
What we can,
excellent.
How we can
Thanks for the comment.
It's all about collaboration, WindEmpowerment.
Yes. I'm not, it's not an ego. It's not. It's just trying to find the best solution for the problem.
Okay. Let me move forward.
Thanks, Esteban. So you're going to arrange it?
Yeah. Let us arrange it later.
All right. Go on, please.
So I'm moving forward to the second part of the presentation, and then we're now talking about the productive uses of the water pump system. So what do we want these systems for? The main goals are family agriculture development. So we need water for family agriculture. This is what we use both in India and in Argentina. We want to improve quality of life of the people living in these rural areas. We want to have a local implementation and maintenance, and we want it to be sustainable financially. So these are the main goals and the main reasons why we are working on this. The main parameters to consider on this are: what is the production? What kind of agricultural production is happening locally? So this will define also what type of irrigation we are needing. What is the area that we want to irrigate? How much water do we need for this particular need? What is the available wind resource in the area? And what kind of wells and tanks do we have? So all of these things need to be taken into consideration when designing the appropriate system, and to answer why are we doing this, and what is the real need that we are trying to meet. So this is the need and the context. In our case, in Argentina, we're talking about a very, very dry area. It's also a very windy area, so this is why we are focusing first in this particular region of Argentina, which is very vast. It has a lot of scarce population, so very few families living very isolated from each other, not big towns, but rural isolated families that live in sort of a desert. The water, as I mentioned before, is not too deep, so it's easy to find in the places where these settlements are. The solar resource of this area is pretty bad because it's a very low latitude, so this is one of the reasons, and it's a very windy region, so this is one of the reasons why this is probably the place in Argentina, not the only one, but the place in Argentina where this technology makes most sense. And we're talking about family agriculture again. So the need of water is not so high. It's for their own production plus an extra production for selling some of their products. So we ran a first pilot project last year. The controller was not ready to be installed in such a remote area yet. So we installed a more standard system with batteries. There are two tanks, one tank higher than the other one, so the water simply goes down from the pumps it to the highest tank, and then it goes down by gravity to the second tank, and from there it goes to the irrigation system. There is an automatic start of the pump. When the highest tank starts to go down, the pump starts automatically to keep the two tanks full all the time. So basically what they do is they manually open and close the valve that goes to the irrigation. So they only open the valves when there is enough energy in the batteries. So basically the batteries, we don't use the batteries as a storage of energy system, but rather as a voltage equalizer. So it's a small battery system. And the pump has to be used, and the irrigation needs to be used only when there is enough wind so that the batteries are full and you have extra wind. This is happening most of the time because there are no other uses of the electricity, and it's a very windy area. So and the irrigation that we use in this particular first pilot project does not use all of the available power of the wind turbine. So it's over dimensioned so that they can make sure that they have enough water for the irrigation system. So why are we focusing on productive uses and maintenance is related to this? Basically, we have a wind turbine that is producing energy. The idea is that this energy is not only for running a TV or for running lights or for their home needs, but rather to create an increase in their economy, in the family economy. How to reach this? Simply by giving drip irrigation to a highest to biggest surface that the family can handle. So not only for their own consumption, but for an additional that they can sell. And this additional increase of income leads to the possibility to have a maintenance fund and to be able to to maintain the whole system financially. So this is the key question of this type of systems. If we're only taking care of the home needs and we do not create an income increase, then it is hard to find in these remote areas and with such rural activities enough income to be able to maintain the whole system. So we did a second project in scale in Patagonia, in the same area, but in a city. This is where the INTA, which is the Agricultural National Institute, they are based in this big city in Patagonia. It's one of their bases. They are all over the country, but one of their bases in Patagonia is here in a scale city. And from here, they develop different agricultural technologies and systems and methodologies that for the different regions of Patagonia, in particular, in our case, for the dry area where we are working, and they are trying to see which type of production they can develop in this area. And one of the main problems they have is the water need, because it's very dry. So which are the expected results of the two systems, both the first pilot project that we already installed with batteries and the one that we are installing in scale for testing together with INTA? Basically, the drip distance along one hose is 20 centimeters. This is the configuration that we're using right now. We have a row length of 32 meters and 0.6 meters between rows. So this is a total surface of 12.5 meters per 32 meters. So that's 400 square meters. This is what we call one module, as this is a standard configuration for one family needs. So this fits their own needs, and it gives them a small extra to have some small income in addition to their own needs. This is one typical module that is being used in this region. In this particular area, they need approximately 5 liters per square meters per day to feed their needs. So for one module, they need 2,000 liters of water per day with drip irrigation, which is the most appropriate technology in the area. What we can supply with the system that we showed before, with the DC brushless motor connected to the 350 watts wind turbine, is approximately 8,000 liters per day in this area because it's very windy. So it could feed up to 4 modules. Now, one thing that is very interesting and that we have learned from INTA is that this particular area could be a very good producer of 2 particular things, which are strawberries and green leaves, leches and those green leaves. So one of the reasons they could do this is because they have the right level of sun, a lot of hours of sun during the summer, and also because they have an offset with the rest of the country, so they would be producing this in a time when the rest of the country does not produce, because they are very far in the south, so they will produce it by the end of the summer. So basically, they would be selling the product in a time when there is lack of this product, so the price is higher. So it has been proven in tests in Patagonia that this could work very well in these dry areas, and the main problem is water. So this is why we are focusing here, because there is a lot of wind, and the main barrier for the development of the area is precisely the need of water for drip irrigation. Now, if one module is enough to keep a family going, with these systems, they could be running up to 4 modules, which would create more than 3 extra modules only for selling, which would be, this is approximately what they could produce. A family has a limitation about their work labor and how much they can, what surface they can tackle for a single family. But since it's individual families all over, we don't need a bigger wind turbine. because we don't need a lot of water in one place. We just need this kind of configuration in very different places because it's scarce population. So this is why we are focusing on this particular technology and this type of configuration, both on the wind turbine and water pumping side, and for this particular application. So which are our next steps regarding this? We are finishing the development of the second prototype, which Jean discussed earlier and explained the details. We have already set a data logger in our test site in Buenos Aires to be able to measure the way this is going to work. We are expecting to do this as soon as possible. We are almost ready to try these tests, so we will be probably starting these tests in 1 or 2 months if there is no more lockout. After the tests in Buenos Aires and after we make it work here where we control it perfectly well, we want to do a test in a scale with production, but in INTA facilities, so not in the middle of nowhere, but in a place where we also control what is happening and to test the agricultural production based on this particular solution. And then to run a first pilot project in the steppe to produce strawberries and green leaves. This will come with other technologies that are coming from INTA. Not only the wind turbine is important, but also their agricultural technology to be able to produce this in such areas. One is the wind fences that we need so that the evaporation of the water is lower. And the second is the microtunnels for the same reason. So this is specific technologies, but here we have to understand that we are not working as an isolated solution for a wind turbine or for a optimal water pumping system, but also for an optimal production in an area where there is the need for this type of technology. So this is it for productive uses and where we're standing today. I'm going to pass it on to Jorge for finishing the presentation on his side. Hello?
Can you open the file, the end?
Yes. Here. Can you see it?
No.
1 minute, because I changed the presenter by mistake, but okay.
No worries. Okay, you can see it now. Hold on. Should be able to see it.
We can't see it yet.
Hold on, I don't know what happened to my computer. It's going crazy.
Anyway, maybe I'll start talking.
But Jorge, I can share it also. Just give me a minute. Okay. Okay. Can you see the screen now?
Yeah, just make it bigger and you can go to the next slide.
Okay.
So in terms of productive uses, we're obviously our goals, in which some of them are already being met. First of all, local manufacture, because we actually built a turbine already on 2 project sites that we've done. The local manufacturer, I'm talking about the wind turbine. Also looking at the lowest cost option, and in this case, the lowest cost option was in fact running an existing system. It's very similar in scope to what's happening in Argentina. Trying to use whatever is local. The one thing that has, of course, we knew we were working in an area that was dry, but our expectations weren't that the drought would continue on for 3 years. So that was basically something that was kind of a surprise for the project. But the last goal here is the multiple uses, and when I'm talking about multiple uses, I'm talking about not only water pumping, but productive applications. The need, as I mentioned before, is of course diesel replacement for much of India to be able to serve in unelectrified or underserved areas. And as a national importance, the ability to make things locally. Can you go to the next slide? Okay, we can skip this. Sorry. The next slide. No, I think. Yeah. Okay. The context in this case is also we're in very dry areas, as I said, the second driest area, and we're dealing with the problem of the drought, which compounds an issue with water supply, even if you're running a solar system. As I say, in this case, the farm that the location we have is a location that has about 5 families living off of one well, and it's basically a experimental farm, you could say, and that's Proto Village, and in their case, the monsoon season had no rain, so you have 3 years consecutively with the same problem. So even having a PV system in the summer, it works because there's sun, but in monsoon season it's cloudy. The solar water pumping system was just not being able to generate enough power to run the pumps. So let's go to the next. Yeah. So what are the options that we're finding with the system? The productive applications are basically, once you finish pumping, what are you going to do? So in the case of Proto Village, the system is designed so that whenever you finish pumping, it's charging the battery bank. So we actually have a 240-volt battery bank. So the wind turbine is switched for priority use between water pumping and battery charging. Now, what is run from the battery bank is basically at this point is a makerspace, which is basically a workshop facility. But the idea is to be able to run directly the additional systems that are needed at the farm. So we've tested at this point the machine shop. So we've been able to run directly from the wind turbine drilling equipment. But what would be most interesting would be something like oil processing. And in this case, this is equipment that's all running with standard 3 horsepower motors. So the one limitation we have at this point is we are any tests we're doing it with either 2 HP or 3 HP motors. But there's another limitation, and that's when a smart controller comes in. The other limitation is we have a cubic relationship for the wind power, but whatever you're using the power for directly from the wind turbine will either have to match that cubic relationship or the power has to be controlled in some way. So our hope is in the future to be able to test some of the applications such as milling, oil processing, and some carpentry, where you would run directly a 2 or 3 HP motor directly from the wind turbine. So you would basically run it battery-less, yeah, and be able to do applications that are in addition to water pumping. Yeah, go to the next. One example of the issue that we're finding in this particular case is the typical growth for this type of environment is are plants that do not require much water. So millets are one of the options that are the traditional plants that were grown before there were any pumps. So these are basically stronger plants that can grow in this type of environment. The only issue that we found, and we've started to look at this, is the machinery to do millet processing is quite antiquated and old. The systems and the motors used are not particularly efficient. And basically, when you go and look at a lot of the machinery, it looks like you're back in the last century. So we're starting to look into developing some applications or modifying some of the equipment so that they may be run with more efficient motors. And in this case, maybe even looking into permanent magnet motors, for example. But for these types of applications, you need a smart controller. So we can see that with Jean explaining the applications possible with the new controller, we can see that these types of new applications can be realized with advances in that part of the project. So can go to the next one. So to conclude, what are the times that we're seeing is, you know, we're in a new time, which is AC, which is after COVID. We're seeing that we're all stuck at home. I think for the most part, those that are listening are basically homebound. And we're discovering that depending on other countries for materials and goods is becoming an issue. So we need to find some self-sufficiency in the way we live and in the way we manufacture. But above all, I want everybody to be safe and be healthy. So thank you for listening, and hopefully we'll have questions after this. Thank you.
Thank you very much, Jorge. And you're right that these times self-sufficiency is more relevant than ever. Okay, so do you want to do the discussion now? Do you have any questions on the presentations? I think there is one question in the chat from Bastien. I think it was during Jean's presentation. So he asks, have you got stat of the type high voltage, high current of converter people are waiting for?
Well, the converter that we are developing is going up to 40 amps at low voltages and is going up to 1000 volts at high voltages with 2 amps. So basically it's a 1 kilowatt power unit that can have both ratings, like both high current and low voltage or high voltage, low current. And so this allows us to switch from the battery zone, battery operating zone with DC appliances and so on, to grid-tied applications or grid voltage level applications. So we strongly believe with such a converter where you can tweak the software and change the functionality with the software side, you can enable all the necessary functions for rural manufacturing, rural productive uses, and rural electrification without having this complexity barrier that prevents you to go for productive uses. For instance, because usually when you think of rural electrification, you deploy some few solar panels and a battery, and the user is not able to do some manufacturing from it. The electrification is bound to the limits of the electronic systems that have been deployed. And what we want to do is from scratch, thinking the electrification from a really low tier of expansion, like from the small DC links that will charge the battery, to the expansion where you finally get into the grid and resell your energy, or provide some energy to drives and motors. So to cover all this range of application. But we are not really waiting for something, we are developing it. So it's not like we are pretty close of having it. I think we will have the first prototype of this ISO power 1 kilowatt converter for by September, sorry.
Okay, any more questions? Somebody is asking if you're going to share the presentations.
Sure, we can share the presentation. There is no issue, I think.
We can include them in the post with the recording, together with your contact emails also, in case somebody wants to follow up with you. Sorry, did somebody...
Yeah, Luis is asking a question in the chat. Will we share the design? Yes, we will share the design. The design is meant to be open source. I think when it will be ended and tested, it will be available both for downloading and reproducing and for usage, but we will also provide a solution to buy it directly. But the idea is to have like the product for sale and all the links, description of functionalities, a bit like Arduino does, for instance, for his microcontrollers.
More questions or comments? Yes, please.
What is your expected price range?
Well, it's a tough question. I guess, like for now, the actual converter that is low voltage only, so it doesn't cover the full range, but is only dedicated to the low range, is about 70 euros. Let's say $80.
Would it be like a low range on under 100 volts or under 200 volts? What would be considered low range?
Low range is so far is lower than 150 volts, but so now like the future version that will have this full range extension and the capability to switch from the battery side to the grid side will be, I think, around a bit less than 200 euros. Like this is the price we want to reach. No, the controller is not Arduino based because Arduino, unfortunately, is limited in terms of calculation power. So we are not able to perform the algorithm with it. So it's based on STM32, which is way more powerful, but yet open source and community-based product as well. So it's a bit like Arduino, but for, let's say, advanced application.
And there is one more question. How do we cater wind uncertainty during design?
I guess this one is for Jorge, right?
Usually what happens is when you're pumping water, you pump to a tank, storage tank. So, and this is what typically happens either both wind and solar is the battery is your actual water tank. That's your storage device. And then little by little, you're able to use the water throughout the day or the week or whatever time period you need. So you obviously need to calculate is how big is your storage tank? What is your what's your wind or solar inputs that you have, and calculate accordingly whatever works well for your installation. But as I say, typically it's a storage tank is what maintains the water, and then you use it throughout the week.
And the next one is a question, I'm not sure. It says module voltage and current rating and frequency. Is the question?
I guess it refers to the converter, but the thing is, it's not fixed. I mean, like you can have low voltage, like under 100 volts with up to 40 amps, or up to 1000 volts and 2 amps. So it's ISO power, meaning that the level of power, the power ratings is 1 kilowatt, but it changes a bit. But yeah, I think it's really a really interesting question. Like what we've seen so far is, okay, my perspective on it is I'm not really in favor of low tech actually, because in my opinion, low tech doesn't usually, well, not necessarily meets the need of the end user. And we are surrounded by technology that we don't understand. For instance, we are all connected through GoToMeeting on a computer. So it's really high-end technology. Though we are still able to connect and we don't have issue with it, even though we don't understand anything of what is inside our computer. I think it's a bit like this with electricity and power application. The end user doesn't really need to understand everything that is inside his converter, but he must be able to connect a local guy that knows how to repair it. And this is like the scheme that is necessary for maintenance in all cases. The thing is, by providing the open blueprints, the open source software and so on, what we want to do is give the knowledge to the local reseller or maintainer that will be able to contact the end user and to take care of his converter and his installation in case of a problem or an issue and so forth. So far.
So there's Ludwig that wants to share shortly about his project. If it is short, I think you can do it now.
Yeah, can you hear me?
Yes.
Yeah, okay.
Yes.
Just like yeah, I'm from the Ernie Collective from Germany, and we're also part of WindEmpowerment. And like I'm also currently focused on water pumping by wind turbine and solar energy, but I'm still on the level that I am using batteries and just switching the pump on and off based on Arduino programmed controller. And yeah, I just want to share that I'm quite interested in this like further controllers, and yeah, I would like to collaborate if that's like possible in future time. And like we are using 230 volts AC deep well water pump, but like yeah, maybe we could connect later on.
Definitely. I think it's really what we are aiming for, like having this stronger and biggest collaboration possible. I think this is the aim of this water pumping project in the end. So with great interest, let's say.
Yeah, like
let's keep in touch and send you emails and organizing a new meeting, because Noam is interested as well to give us his feedback. Maybe you will be able to present your system as well. It would be great to have like new interactions and new participants.
Sure, I would like to. Like I'm still working on it, but it should be. Yeah, I'm really interested in that.
Yeah, I think what you're developing with batteries is also interesting, because in our case in Argentina, we're not completely abandoning batteries, although this is what we're aiming at right now for this particular project. We're also thinking of keeping batteries for other uses, especially in winter or in times where there is no agricultural production and so on. So
yeah,
so definitely is something that that improves, let's say, or makes it more automatic in a way. If it's reliable and robust, it might be also interesting for certain applications in our country as well.
Guys, if I may say, it was excellent presentation. Thank you all very, very much. You know, we've been busy both in the wind turbine and solar for many, many years now. And if you want to have our view of the matter, we'd be delighted to share with you our findings and our philosophy. And, you know, at these hard times when everybody's at home under this coronavirus, and everybody has probably more time to be isolated at home, if you want, please arrange, and I'll be delighted to share our knowledge with you, and be safe.
Okay, thanks a lot, Elad. Thanks a lot, and let's keep in touch about this.
All right.
Sorry, Noam.
All right.
I have a question regarding the electronic controllers. It makes sense to promote it as a GitHub type of project so that more people can get involved. Maybe more technical people and people dealing with software development and stuff like that. Would that make it better or faster to be able to improve on the project?
It's already online. I will be able to share with you the repository where it's based. But yeah, it's a Git-based product. So yeah, it's already open for collaboration. And we will be able to share the details after the meeting, I guess.
Maybe we can include the GitHub link also in the follow-up post, Sam.
Yeah, sure.
Great.
And to rebound on what it was about when we were speaking about batteries, I think a good usage of batteries is not necessarily to store the energy, but just to have this buffer link, just to kick off the startup of the motor. Doesn't have to store a lot of energy, but just to provide the inrush currents to the power application. So this could be just a small battery, let's say.
Yeah, like that's also what we were looking for by using batteries.
More questions? I can't see anything else in the chat. Okay, I think we can follow up later. We can share your emails, and I guess many people have comments and questions. But if you agree, we can end it now. And follow up in another meeting or through emails or in the WindEmpowerment forum as well.
Sure. Thanks everyone for attending, and Caterina for moderating, and Jorge and Luis also for sharing your knowledge.
Thank you very much.
Thank you very much, guys.
For presenting. Thank you for joining.
Thank you, everyone.
Thank
Thanks,
you.
everyone.
And just before you go, if you want to present in a next webinar, you can send us an email with a short proposal, and we can arrange the webinar soon.
Great.
Okay, everyone stay healthy.
Bye-bye.
Bye, everyone.
Bye bye.
Bye, great to see you.